Salam sejahtera everyone. My name is Alexander Sestinus, and together with my group member, Randall Paul, we will present our project entitled Design Optimization of a Hollow Steel Flex Column using Penalty Function Method and Hooke-Jeeves Method. This is our presentation flow, consists of 5 sections. The first is problem context. Second, optimization formulation. Third, algorithm method. Fourth, result. And the last one is engineering interpretation. This is our problem context. Our design aim is to minimize the mass of a hollow steel plate column while keeping the design safe under severe loading. The given loading is column length 10 meter, back load to 4,000 Newton at 9 meter. The wind speed is 169.875 meter per second. And the material structure still is 210 GP. And equal to 7,900 kilo. Okay. And our main design concern is the wind load dominates the bending response. So the final design is governed mainly by normal stress. This is our optimization formula. The design variable are the outer diameter and the inner diameter of the hollow steel tube. This variable determines the cross-sectional area and the moment of inertia of the column. The several structural constraints are included in the optimization model. This includes the allowable normal stress, allowable shear stress, maximum tip deflection of 0.0 meters, and geometric requirements to ensure the tube can be manufactured safely. To solve this constraint optimization problem, we use the penalty function method. This method combines the objective function while the constraint violation into a single equation. When all constraints are satisfied, the penalty becomes zero, and the objective function represents the actual mass of the column. Next is structural calculation. Before performing the optimization, the structural behavior of the flat column must be evaluated. First, the wind speed of 169.875 meters per second is converted into a distributed wind load acting along the fall. From this loading, the total base shear force and base bending moment are calculated. The results show that the distributed wind load contributes much more than the concentrated flake load. Therefore, the bending moment generated by the wind load becomes by the governing factor in the structural design, while the shear stress and deflection remain within acceptable limits. And next is penalty plus Hooke-Jeeves method. The first method is the penalty function method, which converts the constraint optimization problem into an unconstrained problem. If any design constraint is violated, a penalty value is added to the objective function. During the optimization process, the penalty parameter is gradually increased from forcing the solution toward the feasible region. The second method is the Hooke-Jeeves direct search method. Unlike gradient-based method, this algorithm does not require derivative. Instead, it searches for a better solution using exploratory move and a pattern move. The step size is gradually reduced until the optimum solution is reached. And finally, the entire optimization procedure is implemented in MATLAB. The program performs structural analysis, evaluates the constraint, apply the penalty function, execute the Hooke-Jeeves search, and record the optimization history for further analysis. That concludes my presentation on the introduction on this my presentation. I will now hand over the presentation to my teammate who will present the rest. Thank you.
Okay, thank you, Alexander. My name is Randall Paul, and I will explain for you slide next slide, which is coverage behavior. This slide show the optimization process move toward the optimum solution. At the early stage, when the penalty value is still low, the algorithm tend to choose a lighter design. However, this lighter design may still violate some constraint, especially the normal stress constraint. As the penalty value increase, the strain violation become more costly. However, the algorithm start to move toward a safer design, even though the mass becomes slightly higher. This can be seen from the reduction in the maximum constraint violation as the penalty parameter increase. The coverage graph show that the mass increase at the beginning and then becomes stable. This means the design is moving closer to a feasible and optimum solution. In the other word, the optimum process does not only search for the lightest design, but also ensure that the final design satisfy the required safety limits. For that, conclude the coverage behavior. For the next slide is a penalty illustration summary. Summarize the optimization result for each penalty parameter. The main value compared in this table are outer diameter, wall thickness, inner diameter, mass, normal stress, and deflection. For the table, we can see that as the penalty parameter increase, the outer diameter and wall thickness gradually change until they become more stable. At the same time, the mass increase for a lighter but less visible to a safer final design. The normal stress also approached the allowable limit. This show that uh, normal stress is one of the governing constraint in this design. Meanwhile, for the deflection remain well below the maximum allowable limit. This means the deflection is not the controlling factor for the final design. Overall, this table shows that the penalty function method successfully reduced the constraint violation step by step until the design become feasible. For the next slide, this final optimization design. The recommended outer diameter is 0.884 meter. The wall thickness is 0.01475 meter, and the inner diameter is 0.8545 meter. The final mesh of the design is 3,182.099 kilo. For the structural performance, the normal stress is 95.696 megapascal, while the allowable limit is 95.833 megapascal. This means that the design is very close to the normal stress limit, but this is still within the safe range. The normal stress factor of this is 2.403, while it is slightly higher than the minimum requirement value for 2.4. For shear stress, the value is 7.955 megapascal, which is much lower than the allowable limit, 62.5 megapascal. The maximum deflection is 25.859 millimeter, while the allowable deflection is 60 millimeter. This shows that the both shear stress and deflection still have a larger safety margin. Therefore, the final design satisfies all the requirement constraints. For the next slide is discussion and design manning. From an engineering point of view, the results show that bending stress or normal stress is the main factor controlling the design of the flag column. This is because the flag column is subjected to very high wind speed of 380 miles per hour. This wind load produces a large bending moment at the base of the column. Although the optimized design satisfy all constraints in the mathematical model, it is shown to be treated directly as final construction design. In the real engineering application, additional checks are still required. They include local blocking based on a flat design, anchor bolt design, wheel strength, foundations design, corrosion allowance, and last dynamic wind effect. This is important because the model is project focused mainly on mass stress, shear stress, deflection, and geometric constraint. Therefore, the result is more suitable as a mathematical optimization solution and preliminary engineering design. For the last slide, for the conclusion, as we can conclude, this project successfully optimized the hollow steel flag column using the combination of penalty function method and Hooke's law method. The main objective of this study was to minimize the mass of the flag column while ensuring that all design concern was certified. The final recommend design has a mass of 3,182 and with outer diameter of 0.884 meter, while thickness of 0.01475 meter, and the inner diameter of 0.8545 meter. All major concerns were certified, including normal stress, shear stress, deflection, factor of safety, and diameter to thickness ratio. Normal stress and diameter to thickness ratio were identified as the most important constraint in determining the final design. Overall, the combination of the penalty function method and the Hooke-Jeeves method is effective for solving constraint structural optimization problem, especially when gradient calculation is not required. That's all for me.